So today we will be talking about competitive enzyme inhibition. So this is an example of a reversible inhibition. So what happens in this case is, suppose we have an enzyme which binds to the substrate and forms the enzyme substrate complex which can form the product. So in this case, if we have an inhibitor, which I will write it as I, it will bind to the enzyme reversibly, forming the enzyme inhibitor complex. And this enzyme inhibitor complex can no longer form the product. So does this happen in our body? Yeah, obviously. So in our cell we have a metabolic pathway known as Krebs cycle. In one of the steps we have succinic acid, which with the help of the enzyme succinate dehydrogenase forms fumaric acid. We have another compound in our body known as malonic acid, and it has a very similar structure to succinic acid and can compete with succinic acid for the enzyme succinate dehydrogenase. And if these two form a compound, or I would say a complex, then it cannot form the product. So this is an example of an inhibitor. Okay, now we will try to mathematically derive the rate equation for competitive inhibition. Before that, I will write down the steps. So the enzyme binds to the substrate, and in the meantime I would recommend you to go and check out my video on Michaelis-Menten equation, where I have in details described the basic enzymatic equation and also about the steady state approximation, which we will use in this video to derive the equation of competitive inhibition. Okay. So now we can write the rate constant of inhibition Ki as the concentration of free enzyme, concentration of free inhibitor divided by the concentration of the enzyme inhibitor complex. Or we will write down the concentration of enzyme inhibitor complex as EI divided by Ki. We will need this in a later step. So by the steady state approximation, which I described in my previous video, we can write down the rate of change in the concentration of the enzyme substrate complex, which will ultimately form the product, as K1 multiplied by the amount of free enzyme, the amount of substrate, minus K minus 1 to the concentration of enzyme substrate complex minus K2 to the concentration of enzyme substrate complex. So this will form the product. This will go back to forming the enzyme and substrate individually. So as in the previous video I showed that we don't know about this, like at a particular time point when a reaction is happening, we don't know how much free enzyme is left to react. So we will try to get this thing in terms of the thing we know, that is the amount of free enzyme or the total enzyme in the beginning of the reaction and the amount of enzyme that has already formed the substrate or the enzyme substrate complex. So before that we will try to figure this out. So we can write down the amount of free enzyme as the initial amount of enzyme, which is E0, minus the amount of enzyme which has already formed the enzyme substrate complex, minus the amount of enzyme which is bound to the inhibitor in forming the dead end enzyme inhibitor complex. Okay, so we can write this down again as follows: E naught minus ES minus, so here we will put down this thing as I mentioned, so it will be the amount of free enzyme multiplied by the amount of inhibitor divided by the rate constant of inhibition reaction, or we can write it down as Ki into E is equal to Ki into E naught minus ES minus E into I. Okay, now we can take this part to this side and take E as common and write it down as Ki plus the concentration of the enzyme is equal to Ki into E naught minus ES, or we can write down the amount of free enzyme available for the reaction as Ki into E naught minus ES divided by Ki plus the concentration of the inhibitor. So if we divide the numerator and denominator by Ki, we get E naught minus ES divided by 1 plus I by Ki. We will need this a bit later. So now we will try to figure out the rate equation for competitive inhibition. So we can actually take this E and put it down in this equation of des by dt. So I will write the equation for steady state one more time. So it is rate of change of enzyme substrate complex over time is equal to K1 to the concentration of free enzyme to substrate minus K minus 1 ES minus K2 ES. So we will put down E here, so it becomes K1 into E naught minus ES divided by 1 plus I by Ki into S minus K minus 1 ES minus K2 ES. Okay, or we can write this down again further as follows, equal to K1 E naught S divided by 1 plus I by Ki minus K1 ES by S divided by 1 plus I by Ki, and the rest part is as follows. So minus K minus 1 ES minus K2 ES. So now what we will do is we will take ES common from these three terms. So K1 E naught S by 1 plus I by Ki minus E S, take it out of the equation, it becomes K1 S by 1 plus I by Ki plus K minus 1 plus K2. Okay, now from the steady state approximation we know that when there is steady state, the rate of change in the concentration of enzyme over time is equal to 0. So we will just put this down here and we will take this part of the equation to the other side. So the equation becomes ES multiplied by K1S by 1 plus I by Ki plus K minus 1 plus K2 is equal to K1 into E naught S by 1 plus I by Ki. Okay, or we'll need a bit more space, or we can write down ES as K1 E naught S by 1 plus I by Ki divided by, so I will write it down in one line so we don't need a lot of space down, as K1 S by 1 plus I by Ki plus K minus 1 plus K2. So this is the numerator and this is the denominator of this fraction. So now what we will do is we will divide the numerator and the denominator by K1. So it leads us to E naught S divided by 1 plus I by Ki divided by, so this K1 will cancel out, S by 1 plus I by Ki plus K minus 1 by K2 by K1. Now if you remember my video on the Michaelis-Menten equation, I stated there that this part of the equation, so K minus 1 plus K2 by K1, is known as Km, or the Michaelis-Menten constant for a particular reaction. So we'll just write it down here. So this becomes E naught S divided by 1 plus I by Ki divided by S 1 plus I by Ki plus Km. So this Km is K minus 1 plus K2 by K1 for this particular reaction. Never forget this. So what we will do right now is we will divide the numerator and the denominator by 1 plus I by Ki. What we get is E naught S divided by S plus Km multiplied by 1 plus I by Ki. Okay, now as we know, the rate of formation of the product is equal to the change in the product concentration over time, which is equal to K2 into ES. I'm again recommending you to go and check my video on the Michaelis-Menten equation where I've derived all these things in details, so you will get all your answers there probably. So we will just put down the value of ES that we got here, and it's K2 E naught S divided by S plus Km multiplied by 1 plus I by Ki. So now we know that K2 multiplied by the initial enzyme concentration is the maximum rate, or Vmax. So we'll just write it down here, and then this equation becomes this, and I present to you the rate equation of competitive enzyme inhibition. Now as I mentioned you in my previous video, this type of equations are very hard to deal with in a biological lab, because we don't know at which substrate concentration we will get the maximum rate. So Lineweaver and Burke developed a linear plot out of this equation, and what they did is they just took the reciprocal of the left hand side and the right hand side. We will do the same, and it will lead us, or 1 by V is equal to S plus Km 1 plus I by Ki divided by V max into S. And if we elaborate it a bit more, it will become 1 by V max plus Km by V max into 1 plus I by Ki multiplied by 1 by S. So this is the Lineweaver-Burke equation for competitive inhibition. Now what happens is this: suppose we have, let me just draw a graph here. I will just extend this a bit here. Yeah. So in this equation, if the x-axis is 1 by substrate and the y-axis is 1 by the rate, normally what happens in a non-inhibited enzymatic reaction is we'll get a straight line like this, where the y-intercept, this one, is 1 by V max, and the x-intercept, or this one, is minus 1 by Km. Now from this equation, if you look at it, so when 1 by S is 0, then 1 by V equal to 1 by V max. So the y-intercept in competitive inhibition remains the same. And what happens, in competitive inhibition is the Km value changes. So when 1 by V max is, or I would say, 1 by V is equal to 0, what we get is the Km value changes, and it will move further to the intercept, and it will something be like this. So 1 by V max remains same, and the x-intercept becomes 1 by Km into 1 plus I by Ki. Yeah, so this is the basic mathematical treatment for the competitive inhibition. Hope you liked the video and it was helpful, and please let me know down below in the comments if you need something else or if something is unclear, and please don't forget to like, share and subscribe. It really means a lot.